The next speaker is Jack Weber, and we will talk about resource monitoring for Poly ML processes.
Yes, thank you. And this is joint work with Dave Matthews, who is the main developer of Poly ML, and also with Magnus Stenqvist, who is a former student of mine. Our affiliations, for some reason, I think in the printed conference proceedings, they're not quite correct, but Dave is working for a British company called Prolingua now, and I'm employed at Uppsala University, where Magnus was my student. So to motivate this, practically all software that we write is subject to performance requirements. So maybe that's a function that you expect to terminate within a certain number of seconds or minutes, or maybe it's something more complicated, like a server that you would like to support a certain number of clients simultaneously, or whatever it may be. We have these implicit or explicit performance requirements. And to predict the performance of software is quite tricky. So what we typically do is we monitor. We look at our software, we run it, and then we run it under load, and we monitor how it behaves, whether the performance degrades when we have too many clients, or whatever may happen. And that helps us to identify the bottlenecks in our software and perhaps to produce improved versions of it. We can, of course, use generic monitoring tools for that, like the Windows Task Manager or tools like Top or HTOP on Linux. But those tools are somewhat limited in the kind of information that they give you. They can show you things like CPU usage or total memory usage, of course, but they are generic tools, which means they are not aware of the runtime system that your particular application is using. So they can't look into what's happening inside the runtime system. So this presentation is about a graphical monitoring tool for the Poly ML runtime system. We already heard this morning that Poly ML was one of the earliest standard ML implementations. And nowadays, it's arguably one of the most advanced ones as well. So it has a number of very nice features: multi-threading, parallel garbage collection, 64-bit support, you name it. And in particular, what's important for this talk is that the runtime system keeps track of certain statistical information about its own state and makes this information available to other processes that can read that and use that in any way that they want. So the data that we can monitor at present, the data that the runtime system makes available, that includes 17 values distributed across basically 4 areas of interest. We can monitor the CPU time that our process is consuming. We can do this separately for user and for system time, and then for time spent on garbage collection and time spent elsewhere on actual work, presumably. So that adds up to 4 values here. Then we have various values to look into the memory consumption. We can look at the total heap size, at the size of the allocation area, at the free memory in the allocation area, and other things memory free since the last garbage collections. Then we can retrieve the number of garbage collections that have happened in our process, and also we have various values to tell us about the states of the threads that may be running. We get the total number of threads, and we see how many of them may be waiting for I/O, or maybe waiting for a mutex, or maybe waiting for other things, maybe doing signal handling. So these are all things that we can retrieve from the Poly ML runtime system. And on top of that, there are 8 user counters. These are just integer values. And so if you're writing an ML application and you know you'll be running this on Poly ML, you can set these user counters to whatever values you want in your application. Maybe you have a task pool that you want to monitor, and so you could use a counter to well, keep track of the size of your test pool, or whatever else it may be. So at this point, I'll switch to the monitor and give you a brief demo. So let me fire this up. Okay. So this is what it looks like. And when it starts, well, it's showing you the process IDs of all ML processes that you have running on your machine. The monitor application itself is an ML process. So at the moment, we see the monitor monitoring itself, if you wish. It's using a bit of CPU time, as you can see near the top. And I'm sorry that I can't increase the font size, so I try and walk you through. So up here, we see the CPU time that is being used. And it's increasing slowly because obviously our monitor is doing work, monitoring itself. But it's not increasing very quickly, so the scale on the left at the moment is up to 1 second since I've launched it. So fairly low CPU utilization. Then here you see the memory consumption, in particular the red graph is the size of the allocation area. So we see that it keeps allocating more and more memory, which is not surprising because it's acquiring more and more data. Eventually, it would do a garbage collection and forget all the old data, but that's not going to happen anytime soon because this machine has plenty of memory. And then here we see the number of threads. So there are 2 threads in total at the moment, and nothing particularly interesting happening here. And then certainly nothing happening at all with the user counters. They all have initial values of 0. Okay, so let me start a second Poly ML process where we are going to run some slightly more interesting ML code. All right, so now I've launched the Poly ML interpreter from within Emacs, and you see that I have a second process ID in the process monitor now, and if I switch to this second process ID, then this is what you see. It's used a tiny amount of CPU time so far, and all right, so it keeps using a bit of CPU time, but very little really. So there's not much going on at all. We have 1 thread that's waiting for I/O, and that's about it, because the Poly ML interpreter right now is just sitting there idle mostly. So let me start running some ML code. So here's a declaration of a list that has 70,000 elements. So let me execute that. All right, so we got our list. We see this took a little bit of CPU time, again, not much at all. It did increase the size of the allocation area considerably. So here we see the space that our list takes up, and that's all that just happened. Okay. Yes, yes. So this is total CPU time since the process was started. But again, mind the scale on the left. So all of this is, so it's below 0.025 seconds at the moment, right? All right, so we have our list. And here's the straightforward, naive implementation of list reversal that you would expect someone who's just been introduced to functional programming to write, perhaps. So to reverse a list, we reverse the tail of the list, and then we append that to the first element of the list. Okay? So let me declare that function. Done. Again, we see a tiny change in CPU time. We see a tiny change here in the size of the free area in our allocation area. So that's the memory consumed by this function declaration, and nothing else has happened. Okay? And if we now reverse this list of 70,000 elements, finally some interesting things start to happen. So we see the CPU time increasing rapidly here. So we are basically at 100% CPU utilization right now. So it's still running. And if we look at the size of the free space in the allocation area while this reverse function is running, we see interesting things happening here. So we see that the size of the free space is decreasing pretty much down to 0. And then it's increasing again because we are having a garbage collection. So down here we see the number of garbage collections, in this case partial garbage collections. And so we see this stair function here basically where you can see that the number of partial garbage collections is increasing every few fractions of a second. Okay? Right, and now we see that the computation has finished. No further CPU usage. If I go back to Emacs, we see the result of the computation. So this particular call is done. All right, so going back to here, we see from this garbage collection and from the size of the free space in the allocation area that we are creating some intermediate results, some intermediate data structures that are then being garbage collected away. And we are doing this many times. So at this point, perhaps, just by looking at these graphs, we might want to ask ourselves what's going on with this reverse function. Where do all these intermediate data structures come from? And then ultimately, perhaps, could we write reverse in a better way? And of course, the answer is yes, you all know that. But unfortunately, we are not quite getting to that answer just from this graph. But I mean, it can be a first step to investigate further and start thinking about this particular function. All right. So let me terminate this particular Poly ML instance, and let me start up another one. I've written some code to implement the dining philosophers, and I assume you're all familiar with that problem. You have a number of philosophers sitting around a table. Each philosopher has a fork, and to eat they have to grab two forks, the one on the left and the one on the right. But all these forks, they are lying between the philosophers and they're all shared. And so here, I'm setting the number of philosophers to 10. It doesn't really matter. Any number would work, or would rather not work. So these forks are modeled by mutexes, which are provided by Poly ML. I already mentioned it has support for threads and parallel computation. And then each philosopher just grabs the fork on the left and then grabs the fork on the right and then prints that it is eating, and then it releases the fork on the right and then releases the fork on the left. All right, so let's fire up another Poly ML process. And there we go. Here we see it. Again, idle just now. So let me go back to Emacs and run these 10 philosophers. And each philosopher is running in a thread on its own. So we are forking 10 threads here. So the output that we see from our little program Here we go. So we see philosopher 0 is eating 3 times, in fact. Then philosopher 1 is eating, philosopher 2 is eating, and back and forth. So they keep eating, except the output eventually stops, and they are no longer eating, apparently, despite the fact that all these philosophers are infinite loops, and they should keep eating indefinitely. So what's going on? Back to the process monitor. At this point, I started these 10 threads, and PolyML itself has 2 threads when you started. So we can see that we've gone from 2 threads to 12 threads here. But we can also see that pretty much immediately, out of these 12 threads, 10 of them are waiting for a mutex. And of course, you know the Dunning philosophers, so this is not very surprising to you. But once again, it's a nice visualization of the fact that there is a serious problem here. And again, of course, this doesn't quite tell us how to solve the problem, but now we would have to start thinking ourselves. All right. So let me show you a third example where I'm actually using these user counters. Again, let me fire up another Poly ML instance for that. So, right. So here I basically just have a loop that picks a random user counter. Like I said, there are 8 of them. It picks a random one and sets it to a random value, and it keeps doing that. Again, it's an infinite loop. So we pick a random counter, set it to a random value between 0 and 10, and we keep doing that. So when I run that, you can immediately see that the CPU utilization goes to roughly 100%, unsurprisingly. Memory consumption is increasing because it's a recursive function that has some local data structure. So again, this is not very surprising. Eventually, all this data would be garbage collected. But for the time being, we see increasing memory usage. And then after each allocation, we see decreasing free area in the allocation area. All right. And also, down here in particular, we see these user counters, which previously all had values of 0. So as soon as I started this recursive function, they all start moving around wildly. Like I said, values between 0 and 10. So it's quite pretty and colorful, I think. And we can zoom in on that if we want. And so we can see how they are moving around exactly. All right. So those were the examples that I wanted to show you. Can close this. So let me say 1 or 2 words about how we implemented this. The monitoring tool actually consists of a front end and a back end. The front end is written in Java. Oh, the horror. But so like I said, this started out as a student project. And so the student, I think, had a certain preference for certain languages. But there's also a more technically valid reason for this choice. And that is that we didn't really have very good and up-to-date libraries to do graphical user interface programming in PolyML. So there are some libraries to connect PolyML to GTK or whatnot, but they were all a bit dated when we started this, and updating them would have been a project in its own right, which by now we've done, but we hadn't done it when we started this. So it's structured according to the fairly common, well-known model view controller patterns. So we have certain classes that store and manipulate the data, these time series that you just saw, the model classes. Then we have certain classes that render them to the user, that display them in the user interface. And then the controller classes are responsible for dealing with user input. There are certain menu items that I didn't show you in detail. You can change the update frequency, for instance. And so whenever you interact with the code, this goes through the controller classes. Right. In particular, what was very nice was that we didn't have to write our own code to display these time series, but there's a nice Java library that does all the work for us. It's the JFreeChart library, and so all the zooming that I just did and all this automatic scaling of the axes and all that, that's just something we got for free. So this Java frontend launches Poly ML backend, which is just a very small Poly ML process, really. And the only purpose of that Poly ML backend is to request the statistics data for the various Poly ML processes that may be running on our machine. So the front end is sending process identifiers to the backend, and the backend is responding with the corresponding statistics data. And the way that Poly ML makes this data available, well, it is available in a memory mapped file, so you could access this file from your own application directly if you wanted to. We thought about doing this, but turns out that since this was a relatively new feature in Poly ML, the precise binary format of this memory mapped file kept changing, and so at some point we decided it's just easier to use the ML interface, and therefore this Poly ML backend. And so we are using an ML function to get the statistics data. Now, to mention at least one feature of the ML language here, we are using extensible records. This data is returned as a record that has a number of fields. And in this case, that's quite neat, because it means that our monitoring application is forward compatible in the sense that if Dave Matthews ever decides to add more statistics data to this record, our application will still work. Of course, it won't display the new data until you actually change the source code of the application. But it will still work. It will just ignore those fields. Right. So to conclude, we have this application, this monitoring tool. You can use it today to visualize what's going on in your Poly ML and more generally in your standard ML applications. You don't have to change your applications at all. You don't have to modify the code or anything like that. It works on any machine where you can get Poly ML and Java to work, which should be the majority of computers, I guess. And so if you like this, go to this website, download it, try it out, send me feature requests. Thank you. Not from the monitor, so I guess that will be the first feature request.
What's the granularity of which Poly ML is? I mean, so is Poly ML only updating the statistics when you ask for it, or is it constantly updating them?
So my understanding is that for most values, it's constantly updating them whenever they change. Like, say you have a thread that's waiting for a mutex, I believe it's updating at that very moment then, yes. Poly ML, the runtime system, is just writing to a memory map file. So it's not keeping the time series there. It's just keeping the current values there. So the time series that you see is just sampled every however many milliseconds you choose. So I was showing with 500 milliseconds, so twice a second, but you can change that. Yeah, so this JFreeChart library that I'm using actually has a save feature for these time series. So you can save them in, I'm not quite sure what the format is. Yes.